In this video, we shall look at partial derivatives and try to understand how to calculate them. Let z be a function of two independent variables. Let's call them x and y. The derivative of z with respect to x is what is known as the partial derivative of z with respect to x. Why partial? Because now there are two independent variables, x and y. And this is how we write partial derivative of z with respect to x. It's like that. Note that we are using almost a curl d to write down this partial derivative, as opposed to the standard derivative. The interpretation is it is the rate at which z changes with respect to x, while the other remaining variable, in this case y, remains constant. Likewise, the partial derivative of z with respect to y is written like that, which is the rate z changes with respect to y when x remains constant. Of course, there can be three independent variables. For example, let's say u, which is a function of x, y, and z. So here you can define the partial derivative of u with respect to x, the partial derivative of u with respect to y, and the partial derivative of u with respect to z. Let's look at this function. How do we calculate the partial derivative of z with respect to x and the partial derivative of z with respect to y? Let's do the top one first. Remember, when you calculate the partial derivative of z with respect to x, you have to assume y is a constant, or y remains a constant. So that means y just follows, that is this y, and when you differentiate sine with respect to x, you get cosine, but remember there is a y that's a constant there. We can take that out and it becomes y squared, cosine x y. And that's the answer. It's almost as if you are differentiating z with respect to x when z is defined as 3 sine 3x. That's the logic behind it. Now let's do the partial derivative of z with respect to y. So y changes, but x remains constant. We can use product rule. So let's differentiate the y. You get 1. And then the second term follows. In this case, it's sine xy plus. You write down the first term and you differentiate the sine function with respect to y, in a case of which you get x cosine x y. And that's the desired result. What about this function? Let's calculate partial derivative of z with respect to x. So in this expression, a is a constant and b is a constant. Since we are evaluating partial derivative of z with respect to x, so the second term in the argument for sine is a constant. So if when you differentiate the argument with respect to x, you get a. So write that in front, and then differentiate sine with respect to x, you get cosine, and write the argument, ax plus by, and that's the answer. Now let's do partial derivative of z with respect to y. In this case, the first term, the argument of sine is a constant, so when you differentiate this argument with respect to y, you get b. The next step is to differentiate sine. You get cosine, the entire argument. And that's the answer. What about this function? Let's first calculate the partial derivative of z with respect to x. Remember, y remains a constant. So because of that, y just follows like that. And when you differentiate x squared with respect to x, you get 2x. So the answer is 2y cubed x. Now what about partial derivative of z with respect to y? Now the x term is constant, so that will just follow x squared When you differentiate y cubed with respect to y, you get 3y squared. So your answer is 3x squared y squared. And that solves the problem. What about this one? Z is tangent y over x. So the partial derivative of z with respect to x. Note, we have to treat y as a constant. So when we differentiate the argument with respect to x, you get y over minus x squared, because when you differentiate 1 over x, you get minus 1 over x squared. So write that in front. And the next differentiate tangent with respect to the argument. So that's going to give you secant squared of that argument. And that's the result. Now let's do the partial derivative of z with respect to y. In this case, x will remain constant. So when you take the derivative of y over x with respect to y, you get 1 over x. So that's what goes in front. And then, like before, you just take the derivative of tangent with respect to the argument, you get secant squared of that argument. And that's your answer. So when you're doing partial derivatives, it's important to note two things. The first is to recognize the variable that you're differentiating with respect to. And number two is to recognize all the other variables that are to remain constant. Now let's look at this function. What is the partial derivative of z with respect to x? Like before, the argument of that inverse tangent is y over x. Now when you take the derivative of y over x with respect to x, you get minus y over x squared. Step 2 is to take the derivative of inverse tangent with respect to this entire argument, and that is quite simply 1 over that argument y over x squared plus 1. This is simply because whenever you take the derivative of arctangent of theta with respect to theta, the answer is 1 over 1 plus theta squared. So this is what we use to obtain that result. Let's try to simplify this. It is just 1 over x squared over y, I bring this below, times y over x squared plus x squared over y, bracket. So this x squared will cancel that x squared, this y will cancel one of the y there, and you get minus 1 over y plus x squared over y, which you can further simplify as minus y over y squared plus x squared. And that's the result. Don't forget the bracket. Now let's do the partial derivative of that same function with respect to y. Taking the derivative of this argument, y over x, with respect to y, making x constant, you get 1 over x. Now taking the derivative of inverse tangent with respect to the argument, you get 1 over y over x squared plus 1, just like before, which then becomes 1 over x y squared over x squared plus x. So now this x will cancel that x, and you get 1 over y squared over x plus x, which then can be simplified as x over y squared plus x squared. And that's the answer. Let's look at this function. Let's first compute the partial derivative of z with respect to x. Now we can use the quotient rule to do this because it involves ratio. So let's differentiate the top one with respect to x. You get 1. Multiply this with the denominator, x minus y, minus, now differentiate the denominator partially with respect to x. You get 1, and then write the numerator, which is x, over x minus y squared. You see that this x will cancel that x, and what you get is minus y over x minus y squared. That's the result that you're looking for. Now let's do the partial derivative of z with respect to y. So now the numerator, which is x, when you take the derivative of that with respect to y, you get 0. So nothing there. Next, take the derivative of x minus y with respect to y, you get minus 1. Multiply the numerator over the square of the denominator, and you get x over x minus y squared, and that's the answer. Now what about this function? The partial derivative of z with respect to x, again using the quotient rule, differentiate the top, you get 0, minus, now you differentiate the bottom, with respect to x you get n x squared plus y squared, n minus 1, now differentiate the argument, you get 2x, multiply numerator, which is 1, divide this entire thing by the square of the denominator, which is 2n. When you simplify, you get minus 2nx. This over that is just x squared plus y squared n plus 1. Because when you bring the power down here, it simply becomes 2n minus n minus 1, which is just n plus 1, which is that power. And that's the answer. Partial derivative of z with respect to y, again, taking the derivative of the top one, you get 0, minus, now let's do the derivative of the bottom with respect to y, as before, n x squared plus y squared, n minus 1, taking the derivative of whatever that's inside the bracket, with respect to y you get 2y, over the square of the denominator, which is x squared plus y squared, it becomes 2n. And as before, when you simplify, you get minus 2yn over x squared plus y squared to the power of n plus 1. And that's the answer. Let's look at this function, u as a function of x and t. So x and t are the variables, a, p, and b are constants. So let's calculate the partial derivative of u with respect to x. We use product rule. First, take the derivative of that with respect to x. So you're going to get minus a e minus ax. Multiply the second term, which is cosine pt minus bx. Plus, you write the first term, the exponential term, that, and then you take the derivative of cosine with respect to x. In order to take the partial derivative of cosine with respect to x, so first you have to take the derivative of that argument with respect to x. That's going to give you minus b, because those are constants. Now take the derivative of cosine with respect to that argument, you will get minus sine the entire argument. Factoring out the common term, which is the exponential term, you will get minus a cosine pt minus bx. Note that this minus will kill that minus, and the second term will become plus b sine pt minus bx. And that's the answer. Partial derivative of u with respect to t, the first term is just a constant as far as the partial derivative is concerned. Derivative of this argument with respect to t is just p. Derivative of cosine with respect to argument is minus sine of that argument. So your final answer is minus p e to the power minus ax times sine pt minus bx. And that solves the problem. As always, thank you for watching.